Hello, my name is Fatih Furkan Erkeç, and this is machine learning exercise k-means clustering. In this exercise, we will implement the k-means algorithm and use it for image compression. And we will start with a sample dataset that will help gain an intuition of how k-means algorithm works. And after that, we will use the k-means algorithm for image compression by reducing the number of colors that occur in an image to only those that are most common in that image. Okay, let's firstly run this cell. Implementing k-means. K-means a method automatically clusters similar data points together. Concretely, given a training set like that, and we want to group the data into a few cohesive clusters, k-means is an iterative procedure that starts by guessing the initial centroids and then refines this guessing by repeatedly assigning examples to their closest centroids and then recomputing the centroids based on assignments. In this pseudocode, we see the k-means algorithm. In the inner loop of the algorithm repeatedly carries out two steps. Assign each training sample xi to its closest centroid and recomputing the mean of each centroid using the points assigned to it. The k-means algorithm will always converge to some final set of means for centroids. However, the converged solution may not always be ideal, so it depends on the initial settings of the centroids. Therefore, in practice, k-means algorithm is usually run a few times with different random initializations. One way to choose between these different solutions from different random initializations is to choose the one with the lowest cost function value, this option. We will start by complementing find closest centroids and then proceed to compute centroids. Exercise 1, we will complete the find closest centroids. This function takes the data matrix X and the location of all centroids inside centroids. It should output a one-dimensional array IDX which has the same number of elements as X that holds the index of the closest centroid, a value in 0 to k minus 1, where k is the total number of centroids. To every training sample, the index range 0 to k minus 1 varies slightly from what is shown in the lectures. For example, 1 to k, because Python indices start at 0 instead of 1. Specifically, for every example of xi, we set that function, this function that minimizes that. Ci is the index of centroids that is closest to xi, correspond to index I in the starter code, and I think it was pico or nano j is the position value of the jth centroid stored in centroids in the starter code. Okay, let's code in here. Uh, we make a loop and let's create a for loop for I in range x shape 0. We make a distance array and then we made an inner loop for j in range oh, in range centroids dot shape 0 and then norm underscore ij equals to numpy norm and that takes x of I minus centroids j. Then distance append norm ij and then index x index I numpy argmin distance. Yes, should be like this. Let's run it. Let's run well. Let's check the implementation. The code below prints the first five elements in the variable x. And expected output is same. Computing centroid means given assignment of every point to centroid, the second phase of the algorithm recomputes for each centroid the mean of the points that we are assigned to it. Please complete the compute centroids below, recompute the value for each centroid. Specifically for every centroid reset. Okay, where ck is the set of examples that are assigned to centroid k, and ck in the lines is the number of examples in the set ck. Concretely, if two examples say x3 and x5 are assigned to centroid k2, then you should update it like that. Okay, let's write it for e in range k points equals to x idx equal to k, and and uh, centroids k equals to numpy mean points and axis equals to 0. Okay, let's run it. Now we will check the implementation, and here is the expected output. We have an error. Let me check these. It looks like we are correct, but it looks correct, but I will check it where's my problem, and I will continue the video. Okay, I found my error. I write it for I in range, but it should be for k in range, and these k's should be lowercase k, which is used in this k. I mean, it's the index of the loop. Okay, let's run it. And now all tests passed, and in here k means on a sample dataset. After you have completed the two functions, Next step is to run K-means algorithm on a toy 2D dataset to help you understand how K-means works. We encourage you to take look function run underscore K-means below to understand how it works. Notice that the code calls the two functions you implemented in a loop. When you run the code below, it will produce a visualization that steps through the progress of the algorithm at each iteration. At the end, your figure should look like the one displayed in figure 1. The final centroids are the black X marks in the middle of the colored clusters. You can see how these centroids got to their final location by looking at the other X marks connected to it. You do not need to implement anything for this part, simply run the code provided below. Yeah, this is the algorithm, and it calls the two functions we implemented below. Okay, let's run it. Let's run this, and we can see the 2D table. Here is the axis and the different colors of circles, as we can see in here. Random initialization. The initial assignment of the centers for the example dataset was designed so that you will see the same figure as in figure 1. In practice, a good strategy for initialization the centroids is to select random examples from the training set. In this part of the exercise, you should understand how the function K-means underscore init underscore centroids is implemented. The code first randomly shuffles the indices of the examples using NumPy random permutation. Then it selects the first k examples based on random permutation of the indices. This allows the examples to be selected at random without risk of selecting same example twice. Let's run it. You can run k-means again, but this time with random initial centroids. Run the cell below several times and observe how different clusters are created based on the initial points chosen. We made 4 iteration, I think, and this is the iteration number 3. And here image compression with k-means. In this exercise, you will apply k-means to image compression in a straightforward 24-bit color representation of an image. Each pixel represented as 3 8-bit unsigned integers ranging from 0 to 255 that specify the red, green, and blue intensity values. And our image contains thousands of colors, and in this part of exercise we will reduce the number of colors to 16. By making this reduction, it's possible to represent the photo in an efficient way. By making specifically, you only need to store RGB values, 16 selected colors, and each pixel in the image you need only store index of color at location. Okay. We'll use K-means algorithm to select 16 colors that will be used to represent the compressed image. Concretely, we'll treat every pixel in the original image as data example and use the K-means algorithm to find the 16 colors that best group clusters the pixel in the three-dimensional RGB space. Once we computed the cluster centroids on the image, we will then use the 16 colors to replace the pixels in the original image. Let's run it, and we with imread we read the image reads. We read the birdsmall.png on original image, and let's visualize the image in here. Check the dimension of the variable. 128 by 128 and 3 of red, green and blue. Okay, let's process the data. K-means on image pixels in here. The code below will plot all the colors found in the original image as mentioned earlier. The color of each pixel is represented by RGB values, so the plot should have 3 axes, R, G and B. You will notice a lot of dots below representing thousands of colors in the original image. The red markers represent the centroids after running K-means. These will be the 16 colors that we will use to compress the image. We have a small error in here. But it runs. I don't know. I will take that error and let's run it. This is the new palette of the image. Let's compress the image after finding the top K equals 16 colors to represent the image. We can now assign each pixel position to its closest centroid using the find closest centroid function. This allows you to represent the original image using centroid assignments of each pixel. Notice that you have significantly reduced the number of bits that are required to describe the image. The original image required 24 bits, 8 bits by 3 channels in RGB encoding. For each one of the 128 by 128 pixel locations, resulting in total size of this many bits. The new representation requires some overhead storage in form of dictionary of 16 colors, each of which require 24 bits, but the image itself then only requires 4 bits per pixel location. The final number of bits used is therefore this many bits. You can see the difference, which corresponds to compressing the original image by about a factor of 6. And let's run this. Finally, you can view the effects of the compression by reconstructing the image based on the Centroid assignments. As we can see, the colors vanished, but we reduced the image. And run the code below to see how the image reconstructed using the 16 colors selected earlier. Here we can see we compressed the image, but the colors are vanished because we reduced the colors to 16 instead of 24-bit in here. Let me check it. Yes, 3 channels in RGB. Okay, that's it for this assignment. Thank you for watching. Have a nice day, have a nice week.